Welcome to Dart Tutors. Today, we're going to dive into some core concepts in probability, which is a crucial part of the IB mathematics analysis and approaches higher-level curriculum. By the end of this video, you will be able to first, evaluate series expansions related to the Poisson probability distribution. Second, calculate and interpret the expected value or expectation of a discrete random variable. And third, apply the concept of expected value to determine whether games and events are fair. These skills will enable you to solve complex problems in probability and statistics. Let's begin with a question that combines series and probability. Our goal here is to use the Maclaurin series for e to the power of x to evaluate the sum of the series shown. First, recall the Maclaurin series expansion for the exponential function. The formula is e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. This expands to 1 plus x squared over 2 factorial, and so on. Now, let's look at the series we need to evaluate. We have the sum from n equals 0 to infinity of 0.2 to the n times e to the negative 0.2, all divided by n factorial. Notice the term e to the negative 0.2. It doesn't depend on the index n, so it's a constant and can be factored out of the sum. Factoring out the constant gives us e to the negative 0.2 times the sum of 0.2 to the n over n factorial. Now compare the remaining sum with our Maclaurin series for e to the x. Can you see a resemblance? We have the sum of x to the n over n factorial equals e to the x, and here we have the sum of 0.2 to the n over n factorial. It's the same form. The expression inside the sum is the Maclaurin series for e to the power of 0.2. Therefore, the sum simplifies to e to the negative 0.2 times e to the 0.2. Using the rules of exponents, we can simplify this further. E to the negative 0.2 times e to the 0.2 equals e to the power of negative 0.2 plus 0.2, which is e to the power of 0. And anything to the power of 0 is 1. So the value of the entire series is 1. The final answer is 1. This might seem like a clever trick, but it has a deep connection to probability. The expression we evaluated is the sum of all probabilities in a Poisson distribution with parameter 0.2. A fundamental property of any valid probability distribution is that all probabilities must sum to 1. This exercise has proven that this specific distribution is valid. Now let's formally define what we're talking about. The expected value of a discrete random variable. We can think of the expected value as the long-term average outcome of a random experiment. It's often called the mean of the probability distribution. Let's consider a simple example. Imagine a spinner that can land on 10, 15, 50, or 5 points. If these outcomes were equally likely, meaning each has a 1/4 probability, what would be the average points per spin? A naive approach might be to just find the arithmetic mean of the numbers. The sum of the scores is 80, and dividing by 4 gives an average of 20. But what if the outcomes weren't equally likely? This is where the formal definition of expected value becomes essential. For a discrete random variable x, the expected value is calculated by summing the product of each possible value of the variable, x sub I, and its corresponding probability, p sub I. This means you don't just sum the values, you weight each value by how likely it is to occur. It's the mean of the distribution, and it's often represented by the Greek letter mu-im. So expected value equals the sum of x times p. This simple but powerful formula is at the heart of our discussion today. It's important to remember that the expected value doesn't have to be one of the possible outcomes. In our spinner example, the expected value was 20, but you can never actually spin a 20. It's a theoretical average over a very large number of trials. Let's work through an example to see this in practice. A magazine store has observed the number of magazines bought by each customer. Here is the probability table. It shows the number of magazines, x, a customer might buy, and the probability, p, that they buy that number of magazines. Our goal is to find the expected number of magazines a customer will buy and explain what this represents. Remember the formula. The expected value is the sum of x times p. We need to multiply each value of x by its corresponding probability and then add them all together. So, e of x equals 1 times 0.23, plus 2 times 0.38, plus 3 times 0.21, plus 4 times 0.13, plus 5 times 0.05. Let's calculate the products. That's 0.23 plus 0.76 plus 0.63 plus 0.52 plus 0.2. Adding these up gives us our final result. The sum is 2.39, so the expected number of magazines a customer will buy is 2.39. Now, what does this number mean? It doesn't mean any single customer will buy 2.39 magazines. That's impossible. It represents the long-term average. In other words, if we look at a very large number of customers, the average number of magazines purchased per customer would be approximately 2.39. Let's work through another problem that's a common style in the IB exam. Finding a missing probability. We are given a probability distribution, but one of the probabilities, A, is unknown. To solve this, we use a fundamental axiom of probability. For any probability distribution, the sum of all probabilities must equal 1. Applying this to our distribution, the probability of x equals 1 plus the probability of x equals 3 plus the probability of x equals 5 must sum to 1. Substituting the given values, we get 2/5 plus a plus 1/10 equals 1. Now we just need to solve for a. Let's find a common denominator for the fractions. 2/5 is the same as 4/10, so our equation becomes 4/10 plus a plus 1/10 equals 1. Combining the fractions, we have 5/10 plus a equals 1, which simplifies to 1/2 plus a equals 1. Subtracting 1/2 from both sides, we find that a equals 1/2. So we've solved the first part. The missing probability is 1/2. Next, we need to find the mean m, which is just the expected value ex. We use our formula ex. E equals the sum of x times p. Substituting all the values, including the one we just found for a. The expected value is 1 times 2/5 plus 3 times 1/2 plus 5 times 1/10. Multiplying gives us 2/5 plus 3/2 plus 5/10. Let's find a common denominator to add these fractions. The common denominator is 10. This gives us 4/10 plus 15/10 plus 5/10, which sums to 24/10. Simplifying, the mean of the distribution is 2.4. A key application of expected value is in determining whether a game is fair. The expected gain of a player from a game is the expected return or payout minus the cost to play. A game is defined as fair if the player's expected gain is 0. So if we let x represent the player's gain, the game is fair if the expected value of x is 0. In other words, the game is fair if the cost to play is exactly equal to the expected payout. Over the long run, the player is expected to break even. Think about it from the perspective of a casino. Would you expect a casino game to be fair? Probably not. For a casino to make a profit, the expected value for the player must be negative. The expected cost to play must be greater than the expected payout. Let's work through an example involving a game to solidify this concept. In a game of chance, a player spins a square spinner labeled 1, 2, 3, 4. It costs $5 to play. The winnings depend on the number spun. If they spin a 1, they win $1. If they spin a 2, they win $2, and so on. Our tasks are to find the expected return, the expected gain, and decide if we would recommend playing this game. Since it's a square spinner, we'll assume each outcome is equally likely. So, the probability of spinning a 1, 2, 3, or 4 is 1/4 for each. First, let's find the expected return, EY. The expected return is the sum of each winning amount times its probability. So we have 1/4 of 1, plus 1/4 of 2, plus 1/4 of 5, plus 1/4 of 8. This simplifies to 1/4 times the sum of the winnings, which is 16. The expected return is 16 divided by 4, or 4. Now, let's find the expected gain. We know the game costs $5 to play. The expected gain, EX, is the expected return minus the cost to play. So it's $4 minus 5, which equals -$1. Finally, should we recommend playing this game? The expected gain is -$1. This means in the long run, for every game played, you are expected to lose $1. Therefore, no, we would not recommend playing this game. Let's explore another application of expected value, this time in the context of business. An insurance company offers a policy for a $20,000 sapphire ring. If the ring is stolen, they pay the full $20,000. If it's lost, they pay $8,000. Based on past data, the probability of theft is 0.0025 and the probability of loss is 0.003. The company wants its expected return to be $100. How much should they charge for the policy? Let's call the premium P. First, we need to identify all possible outcomes and their probabilities. We have theft and loss. What's the third outcome? The third outcome is that nothing happens. The ring is neither stolen nor lost. Let's define the random variable X as the company's gain for a single policy. The gain is the premium collected minus the payout made by the company. So X equals the premium P minus the payout Y. If there is theft, the company's gain is P minus 20,000. If there is loss, the gain is P minus 8,000. If nothing happens, the gain is simply P, since there's no payout. Now we need the probability of no event. Since the sum of probabilities must be 1, the probability of no event is 1 minus the probability of theft and loss, which is 0.9675. We can now set up the expected gain for the company, EX. It's the sum of the gain from each outcome multiplied by its probability. The problem states the company wants an expected return of $100, so we set this expression equal to 100. This gives us our equation to solve for P. Let's expand and simplify. Expanding the brackets gives 0.25p minus 50 plus 0.03p minus 240 plus 0.9675p. Combining the p terms and the constant terms, we get 100 equals p minus 290. Notice how the p terms add up to exactly p, or 1p. This is because the sum of all probabilities is 1. Finally, we add 290 to both sides to find that the premium P should be $390. This means by charging $390 per policy, the company can expect to make a profit of $100 per policy in the long run. Let's summarize what we've covered today. First, we linked series expansions to probability distributions, confirming that the sum of all probabilities in a valid distribution is 1. Second, we defined the expected value of a discrete random variable, EX, as the sum of X times P. This is a measure of the central tendency of a probability distribution. Third, we applied this concept to fair games, where a player's expected gain is 0. You now have the tools to calculate expected values for various discrete probability distributions, a key skill for IB Maths, AAHL. You can apply this knowledge to solve a variety of problems, from analyzing games of chance to making business decisions. Thank you for joining DAR Tutors. Now it's time for some practice. Here are 5 IB-style questions for you to try. Pause the video and give them your best effort. Question 1. The probability distribution for a random variable X is given. You need to find the missing probability, A, and then calculate the expected value. Question 2. In this problem, you need to first use the condition that the probabilities sum to 1 to solve for K, and then find the expected value. Question 3. This is a classic fair games problem. Calculate the expected value for the player to determine if it's fair. Question 4. This multi-part question requires you to first use the properties of a probability distribution to find P, then find the expected value, and finally compare 2 different games to determine which is better. Question 5. A more complex game. You'll need to define the probabilities for the return from 2 dice, then set up the expected gain and find the value of A for a fair game. Welcome back. Let's go through the solutions. For question 1, to find A, we use the sum of probabilities equals 1. 0.2 plus A plus 0.3 plus 0.1 equals 1. This means 0.6 plus A equals 1, so A is 0.4. The expected value is the sum of X times P. We get 2.5. For question 2, to show K equals 1/6, we write out the probabilities for each value of X. The probabilities are P of 2 equals K, P of 3 equals 2K, and P of 4 equals 3K. Their sum is 6K, which must equal 1. Therefore, K equals 1/6. For the expected value, we sum X times P and substitute K equals 1/6. This gives us 19/6. Question 3 is a fair game question. The player wins $10 with probability 1/6 and wins with probability 5/6. The expected winnings are 10 times 1/6, which is 10/6, or $1.67. The expected gain is the winnings minus the $3 cost, which is negative $1.33. Since the gain is not 0, it's not a fair game. For question 4, we're given the expected value of $3.60 for the first game. The probability of heads is p, so of tails is 1p. Setting the expected value to 3.60, we get the equation 5p plus a 1p equals 3.60. Solving for p gives 0.65. A player would prefer the first game because its expected winnings of $3.60 are higher than the second game's expected winnings of $3.25. Finally, for question 5, we need the probabilities of rolling specific sums with 2 dice. The probability of rolling a sum of 7 is 6 over 36. The probability of rolling a sum less than 5 is the probability of a 2, 3, or 4, which is 6 over 36. For a fair game, the cost A must equal the expected return. The expected return is 8 times 1/6 plus 2 times 1/6, which is $1.67. Therefore, the cost A should be $1.67 for the game to be fair.